Right, chapter 7.3, we're going to take a look at the central limit theorem for sample proportions. So we're going to start with a quick review of what a sampling distribution is. So our sampling distribution we saw on the previous page, or previous section, we looked at values of p hats, and we saw they were between 0%, 25%, 50%, thinking cap people again. And over here we saw probabilities. And for our simulated, or we'll do with the exact one, we saw a distribution looked something like this. Okay. So keep in mind it's a probability distribution for a statistic. We're interested in p hat in this chapter. So probability, it's giving us probabilities on the vertical axes. Shows all of the possible values of the statistic on the horizontal axes. So these are p hats on the horizontal axes. Gives us a probability of each possible statistic. So it tells you how often you can expect to see a particular value over your estimator. So how many or what proportion of your sample results will have each of these values of p hat. Right. Gives you important characteristics of the estimator, such as bias and precision. So our bias was looking at where the center of the distribution was. Precision was looking at the spread. It's used for making inferences about a population. Also allows you to generalize the results of a survey in your sample to a larger group, the population. And it allows you to quantify how far off your estimates are likely to be by calculating the probability that an estimate falls a specified distance from the population value. And we're going to take a closer look at that, those last two in this section. Okay. All right, so number 2, we saw multiple sampling distributions in our previous class. The following is the sampling distribution for p hat. We take random samples of size 4 from a population with 8 students and record the proportion of students that consider themselves cat people. So this is a better version of what I was starting to draw up above. So this is the exact sampling distribution. So you notice that the horizontal axis has the statistic, the p hats, and these again are percentages of the sample or proportion of the sample that were cat people. Again, this is the key. We're looking at the results of a sample. So these are statistics. And over here, we've got our probabilities. So it shows us that the most likely outcome was getting a sample result of 25% cat people, or 1 out of the 4 being cat people. Okay, number 3, we've got an approximated sampling distribution. So this is the following is an approximated sampling distribution for p hat. We take random samples of size 10 from a population with 1,000 students and record the proportion of students that consider themselves to be cat people. It's an approximated sampling distribution in this case, since it contains the results of a simulation, and it had 10,000 repetitions or samples. So keep in mind, in this case, we also had a population. Oops, I need to use p and not p hat. I'm talking about the population with 25% cat people. Okay, so keep in mind this vertical axis right now is labeled with frequency, but it could be relabeled with probability. Remember there were, let's see, 10,000 repetitions and 1,000 students, so 0% here. And up here, 3,000 out of a, let's see, 3,000 out of 10,000 is 30%. And we'll put another couple of numbers on here. This would be 20% and 10%. Okay. So again, relabeling that vertical axis as probability starts to look like the probability distribution we were looking at earlier. Also keep in mind that 0% of the sample are cat people. That also is 0 people, or 0 cat people. And this result here, the most extreme one on the right, 70%. It's the same thing as saying, so your sample size was 1,000. No, I'm sorry, our sample size was 10. Let me correct that. This would be the same as having 7 cat people in your sample. Okay. Right now with the percentages though, this means our horizontal axis is dealing with sample proportions. Okay. Right, we have another approximated sampling distribution in number 4. This is for p-hat when we take random samples of size 100 from a population with 1,000 students and record the proportion of students that consider themselves cat people. It's again an approximated sampling distribution since it contains the results of a simulation. And it had 10,000 repetitions or samples as well. And this again had a proportion in the population that was 25% that identified as cat people. And again, keep in mind this time, our sample size is 100. Up here, our sample size was 10. And again, we can relabel this vertical axis as probability instead of frequency. And this was again out of 10,000 repetitions, so this is 20%, 10%, and 0%. Okay, and taking a closer look at the horizontal axes, and we've labeled it with p-hats. So these are again sample proportions, or the percentage of the sample that identified as a cat person. Or that were cat people. And so in this case, let's see, 10%, our sample sizes were 100. So 10% of 100 at 10 cat people. And here we go up to, looks like maybe we'll take 40% as our example. 40% of 100 will give us 40 cat people. Okay. All right, so number 5, let's compare this approximate sampling distribution when n is 100 students to the previous one with n equal to 10 students. So take a look at both of them. Notice that the center of each approximated sampling distribution is p equal to 25%, indicating that sampling methods are unbiased. Take a look at the second estimator. This is when the sample size is 100. These are much more precise than the previous estimator when n was 10 or the sample size was 10 because the sample size is larger. So by sampling more people, you get more information and end up with a more precise estimate. So I'm going to go back up to both of these, see what I mean by more precise. So keep in mind up here that this went from 0% up to 70%. And the second one, when the sample size was larger, looks like it starts maybe around 12%. And it looks like there might be a bar right there at about 45%. So a little bit less spread, a little bit more precise estimates in the second sampling distribution. And the third bullet down here, the shape of the second sampling distribution is unimodal and a little bit more symmetric. And the last one, there are so many more possible values for p-hat when n is 100 or sample size is 100, that this sampling distribution looks as though it belongs more to a continuous valued random outcome than to a discrete valued random outcome. And so if you take a closer look at both of these, just notice up in this first one, there's some gaps between the bars, making it look like it's discrete. Okay. Second one, those gaps disappear. That's why it begins to look more like a continuous valued random outcome. Okay, number 6, we saw similar results from a simulation in our last group activity. In this group activity, or the group activity that goes with section 7.2, we used an applet to simulate taking random samples of Reese's Pieces and calculating the proportion of orange candies in each sample. The estimator p-hat was unbiased. Both means were very close to p equal to 0.5 for samples of size 25 candies and samples of size 100 candies. This is true for all sample sizes as long as we take random samples. Okay. Precision improved when the sample size increased, meaning the standard error was smaller for samples of size 100. And the third thing is the shape of the sampling distribution was more symmetric for the larger sample size. Okay. Number 7, we turned to simulations in these previous examples because the number of possible outcomes was too numerous to handle. So 2 questions of interest to us today. Are these approximated sampling distributions similar to the actual sampling distributions? Answer is yes, since the sampling methods were random and many repetitions were done. And then the second question, are the results of these simulations predictable? The answer is again yes, which means that we don't need to run a simulation to know what the sampling distribution will look like. Instead, a mathematical theorem called the central limit theorem, or CLT for short, gives us a very good approximation of the sampling distribution. Okay, number 8, we're going to be using the version of the central limit theorem that applies to sample proportions today, or in this section. And we're going to use a version that applies to sample means in Chapter 9. This version can be used when the following conditions have been met. So this version, and we're looking at sample proportions today. So first condition that has to be met for the central limit theorem to be applicable is that the sample is collected randomly from the population and observations are independent of each other. So the sample can be collected with or without replacement. So remember, with replacement means if you take somebody out, let's say an ID number of 1, you put them back in, they can be selected again. Without replacement, you take somebody out that has ID number 1, that ID number can't be used again. That person cannot be selected again. Right. Second condition, the sample size, which is lowercase n, is large enough that the sample expects at least 10 successes, 10 yeses, and 10 failures or nos. And you can check this condition with the following calculations. Take your sample size times the population proportion, and see if you get an answer of at least 10. And both of these have to be met, so keep in mind that and is important. Take your sample size times 1 minus the population proportion, and that also should be greater than or equal to 10. And just a note here, P has to be in decimal form, okay, or fraction form. So second thing here, if you don't know P, and you can make a substitution, you can replace P with P hat. So these are really the same calculation, just making a substitution. If you don't know the population proportion, or the proportion of the population that has a certain characteristic, then you can substitute in the proportion of your sample that has that characteristic. All right, and the third condition, if the sample is collected without replacement, then the population size, note this is capital N, must be at least 10 times bigger than the sample size, and sample size is lowercase n. So you can also check this condition with a calculation. So we've got the population size has to be greater than or equal to 10 times the sample size. If those three conditions are met, then you can use the central limit theorem. So on the next page, if these conditions are met, then the sampling distribution for p hat has, we've got 3 things here, has a shape that is approximately normal, has a mean that's equal to the population proportion p. Remember, mean is telling us where the center of the distribution is. That's because a normal distribution, it's like one of these, unimodal. It's got that single peak in the middle, which means the center should be in the middle. This should be where P is. Okay, and it also has a standard deviation that we can predict. And again, we call this a standard error because we're dealing with the sampling distribution. So standard error is equal to the same calculation we used earlier, square root of P times 1 minus P over N. And again, if you don't know P, if P is not known, then you can do the estimated standard error. So that EST right here means estimated. So putting those all together, the central limit theorem sampling distribution for P hat is a distributed, so remember that means distributed, normally, got the capital letter N there for normal, has a center at P, and has a standard error of P times 1 minus P over N, and taking the square root. So one more note here, that capital N in this notation, remember, stands for the shape, which is normal. So it's just shorthand notation for putting those 3 results together in one statement. And so in picture form, we know that that peak should be right at the middle, should be right at P. Then 1, 2, and 3 standard deviations above, but since we're dealing with a sampling distribution, we're going to call these standard errors. So this is P plus 1 standard error. This one's going to be P plus 2 standard errors. And here P plus 3 standard errors. Over on the other side, same idea. This is going to be P minus 1 standard error. It's going to be P minus 2 standard errors. And here we've got P minus 3 standard errors. And our horizontal axes is labeled as sample proportions. In other words, these are all possible values of p hat. So note that this normal model, and again, this is a model that we're using here, not the results of a simulation, it's just a model of what would happen if we ran a simulation. So note that this normal model becomes more and more accurate as the sample size n increases. All right, so let's check to see if the central limit theorem would have correctly predicted the sampling distributions from our previous simulations. So simulation number 1, where the following is an approximated sampling distribution for p hat. When we take simple random samples of size n equal to 10 from a population with 1,000 students, and in that population we had p equal to 25% cat people, and then we record the proportion of students that consider themselves cat people. It is an approximated sampling distribution, I emphasize that again, in this case, since it contains the results of a simulation and it had 10,000 repetitions or samples. So we're going to start by checking the central limit theorem's 3 conditions first. Remember, the first condition was, are the samples random? We'll put random samples. And are the observations independent? So do we have independent observations? We're going to assume that that one was met because it was a simulation and taking random samples. Second question or second condition, is the sample size large enough? I'm just going to shorten that as sample big enough. So we're going to check that with those 2 calculations. We need to do n times p, see if it's bigger than or equal to 10, and n times 1 minus p, and see if it's bigger than or equal to 10. So in this case, we have sample size of 10. And we had 25% that said they were cat people, so I need to put that in decimal form. Note that I don't get an answer above 10. And over here, I also don't get an answer above 10. You get 0.75. I can clean that up just a little bit. Oops, that should be 7.5. Okay, so we're going to have to put an X here. This condition wasn't met. And then the third condition was the sampling done without replacement or with replacement. So sampling with replacement. Let's put a question mark here. If we're not sure, then we should check those conditions. So is the population more than, population size greater than or equal to 10 times the sample size? So we've got 1,000 people in the population. Is that greater than 10 times 10? And the answer to that is yes. But we do have this one problem here. That second condition wasn't met. So can we use a central limit there? We're going to have to say no. It's not going to work in this case. The model that the central limit theorem predicts isn't going to be a good fit for what actually happens with the simulation. So I've recopied the simulation results here. And what we're going to do on the right is show what the central limit theorem's model would have predicted if the conditions had been met. Right, so it's going to predict the shape is normal. It's going to predict the center to be at 25%, or 0.25 if you want to do this in decimal form. So again, keep in mind that the horizontal axis here is sample proportions, just like in our simulated results. So sample proportions, or p hats. And the standard error, we would get, let's do p times 1 minus p, and 1 minus 0.25 is 0.75. And our sample size was 10. Gives a standard error of about 0.1369. And so if I put in a few more numbers on my axes, in particular, let's look at 3 standard errors away from the center. So I'll leave it up to you to double check this. But if you multiply this standard error by 3 and add it to the center, you're going to get 66.07%. Over here on the end, you're going to get a negative number, negative 16.07%. And notice those aren't doing a very good job of predicting where this distribution started on the left. somewhat similar to where it ends on the right. But the other part that falls that's not correct is the shape. And here, try and superimpose that, it might look something like this. Notice that the shape is not correct. So central limit theorem was unable to predict the shape of what happened with our simulation because the sample size wasn't large enough. And again, the model doesn't fit. So did the central limit theorem accurately predict the results of the simulation? We're going to have to say no. And so keep that in mind. If your conditions aren't met, then something's not going to work. The model's not going to work. It's the sample size, it's the shape that doesn't work. And so simulation number 2. Following is again an approximated sampling distribution for p hat when we take simple random samples of size n equal to 100 from a population with 1,000 students. And again, p, population proportion, was 25% CAP people. And we recorded the proportion of students that consider themselves CAP people. It's again an approximated sampling distribution since it contains the results of a simulation with 10,000 repetitions or samples. So let's check those conditions. So again, we want to double check where random samples collected and were the observations independent of each other. So we're going to say that has been met. That question is yes. So we're going to check sample size. So is the sample size large enough? So if we do n times, and n in this case is 100, n times p, notice we get 25. And if we do n times 1 minus p, we get 75. So since these are both greater than or equal to 10, we can say this condition has been met. And then the last one we want to check, because we're not sure if with replacement or without replacement, we want to see if the population size is at least 10 times bigger than the sample size. So in this case, it's 1,000 greater than or equal to 10 times 100. And in this case, because our sample size was 100, that's been met. Good thing there's that equal sign here. You get 1,000 on the left, you get 1,000 on the right. All right, so can we use the central limit theorem? Answer is yes. All right, so let's take a look at what the central limit theorem would have predicted and if that model would have fit the simulated results. All right, so first thing, we know the shape central limit theorem predicts is normal. Second thing, we know the center should be at P. It's at 0.25. I'm going to switch that to 25% so it matches the scale used on your approximated distribution from your simulation. And again, this are sample proportions on your horizontal axes, or p hats. All right, so next up, we've got to check how spread out these are. What's our standard error going to be? So we're going to take p times 1 minus p, which is 0.75, and divide that by the sample size of 100. And notice our standard error is a bit smaller than the previous one. It's about 4% or 4.33%. So if we put a few more values on the axes down here, and in particular, I'm going to look at what's 3 standard errors away and what's 3 standard errors to the left and the right of the center. So we'll put a few more values in. We'll put 29.33, that's 1 standard error above. And then we've got 33.66% here and 37.99% here. You can double check this, grab a calculator and try it out for yourself. This, if I take 25% and subtract 1 standard error, get 20.67%. Here it's 16.34%. And here it's 12.01%. All right, so how did this do? Well, it looks like here the shape is accurate. Looks like the center was predicted well. It's at 25%. It looks like it starts on the left around 12% and ends on the right. Looks like that's our largest value, right around 38%. So it looks like the model fits. So again, what this tells us is that the central limit theorem would have predicted or did a good job of predicting what the simulation produced. So did the central limit theorem accurately predict the results of the simulation? We can say in this case, yes. We can also say that the sampling distribution for p hat is, and I'll put that tilde sign for distributed. Let's see, I'm going to have to move this over a little bit. Is normal, so that's its shape, centered at 0.25 or 25%, and has a standard error of 4.33%. Okay, so some observations. In the first case, the sample size was too small for the central limit theorem to apply. In this case, the simulated sampling distribution does not look normal. It was not symmetric. In fact, it was right skewed and had large gaps between values. The simulated sampling distribution is shown below, and the diagram was also shown on page 318 of your textbook. So again, notice it's not symmetric. In fact, it's skewed to the right. So this is not the same shape. The shapes are different. In the second case, all three conditions were met and the central limit theorem applied. So the simulated sampling distribution looks very close to the normal model predicted by the central limit theorem. The diagram below shows the simulated sampling distribution with the normal model superimposed. And again, you can look at page 318 of your textbooks to see this graph. Okay, so we've got our normal model here in red. That's that normal model on top. And we've got our simulated results. That's the histogram below it. And that provided a good fit. Again, that meant the central limit theorem correctly predicted what would happen if we ran the simulation. And note, the central limit theorem correctly predicted the mean of both sampling distributions. So the center of both were at 25%, but the shape wasn't correctly predicted in the first one. Also, the sampling distribution for sample size n equal to 100 had more precision than the sampling distribution for sample size of 10. So again, precision talks about spread. So notice that this distribution is quite a bit more compact. It goes from about 10 to 40% than this one. This goes from about 0 to 70%. Okay, number 11, let's take a look at one more simulation. Following is an approximated sampling distribution for p hat when you take random samples of size 100 from a large population of Reese's Pieces. That has p equal to 50% orange candies. And then you record the proportion of orange candies in each sample. It's again an approximated sampling distribution since it contains the results of a simulation, and it had 10,000 repetitions or samples in that simulation. So let's check the conditions. So can we assume that these are random samples? Most likely, yes. And are they observations independent of each other? Again, most likely, yes. Each candy was chosen independent of other candies. All right, second thing, sample size. Is the sample size big enough to use the central limit theorem? So if we take n, we've got, let's see, samples of size 100, here's our n, times p. P is 0.5, we get 50. And if we do n times 1 minus p, notice we also get 50. So good news, both are greater than or equal to 10. So we can say that these have both been met. And then that third one, you need to check if your population size is greater than or equal to 10 times your sample size. Well, in this case, we don't know what the population size is. We don't know how many Reese's Pieces there actually are. But if we do 10 times our sample size, which is 1,000, we can probably safely assume that there are more than 1,000 Reese's Pieces out there. So it looks like, yes, we can use the central limit theorem. All right, so what would they have predicted for a model? So they would have predicted that the shape, the central limit theorem would predict that the shape is normal, that it would have been centered at 0.5. In this case, again, we're looking at sample proportions or possible values of sample proportions on the horizontal axes, or p hats. And then we also need to know how spread out these are. So the standard error would be 0.5 times 1 minus 0.5 over 100, which is equal to 0.05. So if you go out 1, 2, 3 standard errors to the left and right, this would be 0.55, 0.6, 0.65. If I subtract going in this direction, we've got 45% or 0.45, 0.4, 0.35. All right, so that do a good job of predicting this model. Looks like 0.35 is roughly where it starts on the left. 0.65 is roughly where it starts on the, or stops on the right. Shape looks good. And the center looks like it's right around 0.5. So the central limit theorem accurately predicted the results of this simulation. You can say yes, it did. And the model is a good fit for what actually happened in the simulation. Okay, so a reminder, a probability tells us how often an event will occur if we repeat an experiment an infinite number of times. This means that the sampling distribution for p hat gives us the probabilities of where our sample proportions will fall. That is, it tells us how often we would see particular values of p hat if we could repeat our survey infinitely many times. So it can also tell us how likely it is that we'll find a particular p hat or a p hat within a given interval, how likely it is that we'll find a p hat greater than a particular value, and how likely it is that we'll find a p hat less than a particular value. All right, so let's take a look at how the central limit theorem can be used to answer these types of questions. So how likely is it that our p hat will be within a given interval? So let's return to our population of 1,000 people with 25% cat people. I've already checked that the conditions of the central limit theorem have been met when the sample size is n equal to 100. So let's draw the normal model for the sampling distribution for p hat. So instead of running the simulation, we're going to just turn to what the central limit theorem tells us or predicts will happen. So we know the shape's going to be normal. We know it should be centered at 25% or 0.25. And we know that the standard error should be p times 1 minus p over n. Our sample size is 100, which is 0.0433. So if we go 1, 2, and 3 standard deviations to the right, 1, 2, and 3 standard deviations to the left, and again, double check these numbers, grab a calculator and try this. We should find that the lowest value on the left is around 12%. And over on the right, it's like the larger values are going to be around 37, 38%. So keep in mind, I didn't leave myself enough room here to label the horizontal axes, but the horizontal axes are giving you possible values for sample proportions, or in this case, and p hats. Right, so now we're going to use this normal model to find the following probabilities. So we want to find the probability that you get the proportion of cat people in your sample, or a proportion of cat people in our sample greater than 26%. So greater than 26%, 26% is right here on our axes. So we're interested in this area to the right. This is where our work in chapter 6 starts to come in. We can take this score, or this proportion, and standardize it. So we're going to figure out how many standard deviations 0.26 is from the center of the distribution. So we're going to subtract, and then we're going to divide by the standard error. And that's going to give us a z-score of 0.23, or 0.23, which means we can now use our tables and figure out what's the proportion of z-scores, or what's the probability that we get a z-score greater than 0.23. And that is equal to 0.4090. And just a reminder here, if you haven't done this in a little bit while, you need to subtract the area from your chart to get this number, or look up negative 0.23. All right, next one, we're going to find the probability that you get a p hat less than 20%. So again, we're going to standardize this. Note that 20% is right around here, so we're looking for this area in our distribution. So we're going to take 0.20 minus the center, divided by the standard error. We're going to get a z-score of negative 1.15. So we need the probability of getting a z-score less than negative 1.15, which we can take directly off the table, which is 0.1251. And then the last one here, we want to know what's the probability that we get a result, a sample proportion between 15 and 30%. So now we're going to need two z-scores here. So our first z-score is 0.15 minus 0.25 over 0.0433. We can double check this, but you should get a z-score of negative 2.31. And our second z-score is equal to 0.30 minus, again, the center, 0.25, over the standard error, which gives us a z-score of 1.15. So that means we can use our table to find the probability of getting a z-score between negative 2.31 and 1.15. And I'll leave it up to you to verify this, but you should get an answer of 0.8645.